Hello. So I'm Fiona Chapman. I'm a PhD student at INRS in Quebec City, but my project is in partnership with the Yukon Geological Survey, with a lot of support as well from the Kalani First Nation, whose traditional territory we work on, and who potentially could be influenced by our findings. So the title of my presentation was a heat flow assessment with fiber optic cables in a 385-meter well in southwestern Yukon. We're just going to add on to that. In fall last year, a second well was drilled in the area by the Yukon Geological Survey, which is 220 meters deep. And it's relatively close, but there's quite a few differences. So throughout the presentation, we'll talk a bit about why these differences are important, and the results from both of these wells. So the overall objective of my project, it will be ultimately to evaluate the geothermal potential around the community of Burwash Landing in southwestern Yukon. So what does that mean? In general, we're thinking about conventional geothermal systems. So as we know, there's three factors to that. We have our need for permeability, we have our need for heat, and we have our need for fluid. Last field season, I concentrated on the permeability aspect. So I walked around essentially Kalani National Park, measuring cracks in the rocks. And then this year, we're going to focus on the heat aspect by assessing the in-situ thermal gradients and the thermal conductivities of sediments and rocks in the area. And it's the gradients and the conductivities that will allow us to estimate the heat flow. So Burwash Landing is located in southwestern Yukon at the base of the St. Elias Mountains. And for those of you who, I don't know, are familiar with Mount Logan is part of the St. Elias mountain range. And Burwash Landing is at the base of the mountains, situated along the Denali Fault and adjacent to Kalani Lake, which is a lake that's 80 kilometers long and 30 kilometers wide in the area. So one of the motivating factors for this research was this high topographic gradient and the permeable zone that is the damage zone of the Denali Fault. So the idea being, okay, permeability-wise, the water could be coming up through the damage zone. The fluid should be available. There's a big lake, there's water, there's mountains. It all makes sense. But what about the heat aspect? So in northern areas or in remote regions in general, there's typically an issue with data availability. So if we consider southwestern Yukon, which we defined as a 200-kilometer box, which goes past Carmacks and down past Whitehorse, in that area, there are two heat flow values available, both of which are right next to Whitehorse. So rather than using those values, we took a step back and looked at the Curie point depths. So the Curie point depth is the depth at which rocks lose the magnetic properties, and it's useful because you can use remote sensing or aeromagnetic surveys to get these results. And from this popped out that, okay, let's look. The Curie point depth is shallower in this area. Why is that? Is it true? Is it an artifact? Can we use this information? So this is what sparked the interest with respect to heat in the area. And then we went on site to measure the thermal gradients and the in-situ properties. So we have these two wells. The first one was drilled by Kalani First Nation right in town in 2012. And it was drilled, a temperature profile was measured, and then nothing happened. The Yukon Geological Survey started a project in 2018, which led to drilling a second borehole on the other side of the Denali Fault. So our first one is in Burwash on the north side, and our second well is along the Duke River, which is on the other side of the Denali Fault. This location was chosen to try and get trying to understand the difference of the sediments and rocks on either side of the fault. And also the seismic guys were really excited to hope that that well crossed the fault. Anyways, we measure the profiles. So in the Burwash well, we have a temperature gradient of 47 degrees Celsius per kilometer. And then not too far on the other side, the Duke River well has a temperature gradient of 34 degrees Celsius per kilometer. This seems quite a significant difference. The reasoning for this is that the Burwash landing well is entirely in sediments with very low thermal conductivity, whereas the Duke River well enters bedrock after just 40 meters. And we'll put numbers to those comments in just a moment. So how do we measure the thermal conductivity? We measure the thermal conductivity by using a heat injection test. So we inject heat, we record temperature during the recovery process and the injection process. Instead of trying to explain this here, I'm going to take you on a tour of our study site. It's a little cringe, but hopefully it's worth it.
Welcome to our study site on the traditional territory of the Kwani First Nation. We're here doing a heat injection test in a well drilled by the Yukon Geological Survey in October 2022. This well is 220 meters deep and is part of our larger project that involves assessing the geothermal potential around southwestern Yukon. Once we have our temperature profile, we can start our heat injection. The heat injection test is designed to let us measure the thermal properties of the different lithologies that this well passes through. We'll be injecting heat for 2 days, and then we'll follow the recovery process for the following 4 to 5 days as the well recalibrates and the rock come back to their standard temperature. This setup uses fiber optic cables to measure temperature throughout the well. In the junction box, they're paired with a copper wire through which the heat is injected. This black cable contains the fiber optic cables and the copper wire and is lowered 200 meters down towards the bottom of the well. This structure lets us lower the cable and keep it steady throughout the experiment, including the heat injection and the recovery process. Let's go see what the cables are actually hooked up to inside the trailer. In here, there are 3 main components. Let's start with the heating component. This is our heat pulse, and it's what injects the energy into the copper cable down the well. It's connected outside to a generator, which is 480 volts and up to 20 kilowatts. That generator, combined with this heat pulse, lets us inject roughly 28 watts per meter all the way down our well, heating the water and the surrounding rock equally for the whole 2 days of injection. Down here, we have the fiber optic component. So this black box is a digital temperature sensor, and it sends a laser down the blue fiber optic cable and into the well. And the response is what allows us to measure temperature at 25 centimeter intervals throughout the whole fiber cable. This measurement is taken at each of these points every 3 minutes for the whole duration of the test. That means it starts before we start injecting heat for our initial profile. It continues to record temperature for the 2 days of heat injection, and then it keeps going for the last 4 to 5 days, measuring the recovery as the ground comes back to equilibrium. Now, the fiber optic cable is great, but it's not perfect, so it goes through a calibration bath, and that's what we're going to look at next.
Calibration bath, for the sake of time today, but if anyone's really curious about it, we can definitely chat about it later. And move on straight to the data analysis. So we did that test in both wells, so in the well in Burwash and the well at Duke River, and we got 2 different temperature profiles because in 2 different settings. And you'll notice that on the Burwash results, we have 4 different lines. This was the first time we were using fiber optics to take these measurements. Normally we do them in shallower wells, and then we simply use STOROD temperature loggers to record temperature, which are great, but it wouldn't let us have as high frequency data as the fiber optic cable did. The reason why we have these on the Burwash well and not on the Duke River well is the Duke River results are from last week, so we just haven't quite gotten there yet. But essentially, from our test, we found that the thermal conductivity in Burwash landing, so in the sediments, is around 2.1 watts per meter Kelvin, and then the thermal conductivity of the bedrock, in which the Duke River well penetrates, is 3.4 watts per meter Kelvin. The difference between these values, as I mentioned, it was the first time that we've used the fiber optic cable. And as you saw in the video, the fiber optic cable is encased right next to the copper wire. And we noticed that during the injection phase, the fiber optic results tended to overestimate the thermal conductivity and underestimate it during the recovery. So when it was averaged out, we had similar results to our regular temperature loggers. But this is something that we believe is due to the fact that it's insulated by the extra cable and held in such close proximity to the copper wire. So that is something that we're going to work on developing a solution to correct for. So we can have both our high spatial resolution from the fiber optic results, but also to make sure our profile is actually representative of the rocks and is less impacted by the insulation. That brings us to our heat flux calculation. It's kind of like the moment of truth. Your heat flow or heat flux is simply your temperature gradient multiplied by your thermal conductivity. So we now have both those values for the study area. And our Burwell standing results give us a heat flow of just under 100 megawatts per meter squared, and then 115 for the Duke River area, which is quite exciting. The only other values that we had for southwestern Yukon, like you mentioned at the start, were just around Whitehorse. And those values, around Whitehorse, there's a heat flow values that averaged 63.5 megawatts per meter squared. So this is significantly warmer and quite interesting for the next steps in evaluating the potential. So what are the next steps? Last year, we focused on permeability. This year, I focused on heat. And then hopefully by next year, I'll be able to present a complete model to you that considers the regional flow and the heat transfer mechanisms in the area. So that's where the project is going. Something that we are working on the side is our social acceptability project. So I think it's very important to keep in mind that geothermal energy is a local energy, where it's not something like oil and gas that we can transport far. If we're using it locally, which means we need to have people who need it and people who are interested in using it. So we're working with Kate Balaguin, who's the natural resource manager for the Kalani First Nation, to sort of understand how community members perceive geothermal energy and see where this research can fit into their future visions for their energy budget. And with that, I'm happy to take any questions.